Matter is composed of atoms and molecules which are constantly in motion. This motion is directly related to the amount of heat energy in a body. The heat energy in a body determines in which of the three states matter will exist: solid, liquid, or gaseous. Water may exist in all three states: as a solid, ice; as a liquid, water; or as a gas, steam. Molecular motion may be illustrated with the help of a glass tube. Inside the tube are bits of colored glass and a small quantity of mercury, a metal that is in the liquid state at room temperature. As the tube is heated, the temperature of the mercury is raised until some of it changes to a gas. As the temperature continues to rise, the molecules of mercury vapor begin to move more rapidly, bouncing the bits of glass around until the action of the mercury molecules becomes violent. Both gases and liquids are classified as fluids. Both have weight. Both may be used to transmit power. However, each has individual distinguishing characteristics. Gases are compressible. For practical purposes, liquids are considered to be incompressible except under special circumstances. Temperature is a measure of heat energy in matter and is measured in degrees on a thermometer. The temperature scales with which most of us are familiar are the Fahrenheit and Celsius or centigrade scales. Water freezes into the solid state, ice, at 32 degrees on the Fahrenheit scale or 0 degrees on the Celsius scale. Water boils and turns to water vapor at 212 degrees on the Fahrenheit scale or 100 degrees on the Celsius scale. There are 180 divisions or degrees between the freezing point and the boiling point of water on the Fahrenheit scale, and 100 degrees between the same 2 points on the Celsius scale. To convert a temperature reading from the Celsius scale to the Fahrenheit scale, remember there are 100 Celsius degrees in the same temperature range of 180 Fahrenheit degrees. Multiply the Celsius temperature by 1.8 and add 32 degrees, since the Fahrenheit scale starts 32 degrees lower than the Celsius scale. Another popular formula for the same conversion is the Fahrenheit temperature equals 9/5 times the Celsius temperature plus 32 degrees. To convert from Fahrenheit to Celsius, first subtract 32 degrees from the Fahrenheit temperature. Then divide the remainder by 1.8. The popular formula for this conversion is the Celsius temperature is equal to 5/9 multiplied by the quantity the Fahrenheit temperature minus 32. The temperature and pressure of fluids are often measured in reference to absolute scales. In the early part of the 19th century, the French chemist Joseph Louis Gay-Lussac discovered that when the temperature of a gas was raised from 0 degrees Celsius to 1 degree above zero, its volume increased by 1/273rd. Gay-Lussac surmised that a decrease in temperature would produce a corresponding decrease in volume. He concluded that reduction in temperature to minus 273 degrees Celsius would decrease the volume of a gas to zero, the point at which all molecular motion ceases. Minus 273 degrees Celsius is considered to be absolute zero. A temperature scale beginning at absolute zero was named the Kelvin scale. To find Kelvin temperature when the Celsius temperature is known, simply add 273 degrees to the Celsius temperature. Another scale relating absolute zero to the Fahrenheit scale is the Rankine scale. Absolute zero on the Rankine scale is 460 degrees below zero on the Fahrenheit scale. To find the Rankine temperature when the Fahrenheit temperature is known, add 492 degrees to the Fahrenheit temperature. Water freezes at 492 degrees on the Rankine scale. Let's consider some facts concerning pressure and its effects on gases. As you sit in your classroom viewing this program, you're surrounded by an ocean of air. In fact, you're sitting on the floor of this ocean with the weight of a column of air about 500 miles high, exerting a pressure upon every square inch of your body. That air has weight may be demonstrated by weighing a container of air, then attaching the container to a vacuum pump, and evacuating some of the air. You'll see that the weight of the container is less than before the air was evacuated. The weight of a column of air 500 miles high and 1 square inch in area is about 14.7 pounds. This is atmospheric pressure. Pressure is defined as a force per unit area and is usually measured in pounds per square inch. Atmospheric pressure is the weight of a column of air extending from sea level to the outer limits of the atmosphere. The pressure will vary depending upon the actual height of the column. That height changes continuously. Standard atmospheric pressure is 14.7 pounds per square inch, absolute. Atmospheric pressure is given in absolute value because it is referenced to zero pressure. The pressure which you normally read from a pressure gauge is measured in pounds per square inch gauge, or PSIG. The zero reference on most pressure gauges is actually 14.7 pounds per square inch absolute. A gauge that reads in absolute pressure will show a reading of 14.7 pounds per square inch at sea level. To convert from gauge pressure to absolute pressure, simply add 14.7 pounds per square inch to the reading on a standard pressure gauge. For instance, the tire pressure on the nose gear of a Cessna 210 is 50 pounds per square inch gauge. That translates to 64.7 pounds per square inch absolute. The pressure readings on nearly all pressure gauges in an aircraft instrument panel are shown in gauge pressure. The pressures given in manufacturers' service manuals are gauge pressures. Pressures may also be given in inches of mercury, or in the case of very low pressures, inches of water. Pressure in inches of mercury is derived from the pressure of the atmosphere, 14.7 pounds per square inch, acting on one end of a tube of mercury, with the pressure on the other end of the tube reduced to zero. The atmospheric pressure, working against the weight of the mercury, will force the mercury to a specific height inside the tube. At sea level, standard atmospheric pressure will raise the column of mercury to 29.92 inches. If the same experiment were conducted at a higher altitude, say on the top of a mountain 2,000 feet above sea level, the column of mercury would rise to only about 27.82 inches. That's because as you go up in altitude, the height of the column of air producing atmospheric pressure decreases. The pressure drop is about 1 inch of mercury for every 1,000 feet of increase in altitude. The process used to measure the atmospheric pressure in inches of mercury illustrates an important principle, without which there could be no flight. That is, the principle of differential pressure. The height of the column of mercury is the result of the difference in pressure between the vacuum in the top of the tube and the ambient or atmospheric pressure. The principle of differential pressure is also partially responsible for fuel flowing through the carburetor of an aircraft engine. It also is an important part of the aerodynamics of flight. Both of these concepts will be explored in other programs in this series. Differential pressure may be measured from any reference point. Differential pressure is, as the name implies, a difference between pressures. This illustration shows a differential pressure of 3 pounds per square inch. However, that differential pressure may be measured from anywhere on the pressure scale. The aircraft airspeed indicator is a differential pressure gauge. The instrument measures the difference between the high ram air pressure on the pitot tube, caused by the movement of the aircraft through the air, and the static pressure, the atmospheric pressure of the still air around the aircraft. Although the instrument is actually sensing differential pressure, it's marked or calibrated to read in knots or miles per hour. The greater the pressure difference, the greater will be the needle deflection, and the higher will be the airspeed indication. A gas is a fluid that takes the shape of its container and expands to fill the container completely. Changes in temperature, pressure, and volume occur in a confined gas with a definite relationship between all three characteristics. This relationship was expressed by the 17th century physicist Robert Boyle and an 18th century physicist named Jacques Charles. Boyle discovered that the pressure of a confined gas varies inversely with its volume if the temperature is held constant. This partially filled balloon is placed inside a laboratory bell jar. The air is evacuated from the jar by a vacuum pump. As the air pressure drops in the jar, the air confined in the balloon expands. The pressure in the bell jar continues to decrease, and the volume of the air in the balloon increases. As pressure is allowed to return to the bell jar, the volume of the air in the balloon again is reduced. This relationship of pressure and volume may be expressed as a mathematical equation. V sub 1 divided by V sub 2 is equal to P sub 2 divided by P sub 1. V sub 1 is the volume of the balloon under normal pressure. P sub 1. V sub 2 is the volume of the balloon after the pressure has been reduced. P sub 2. As pressure decreases, volume increases. Charles defined the relationship between the temperature of a confined gas and its volume. He discovered that the volume of a confined gas varies directly with its temperature. If a container is filled with a certain volume of gas and the temperature of the gas is increased, the volume of the gas will also increase. Here we have a container with air confined in the top. The container is attached to a tube partially filled with liquid. The tube is immersed in a container of liquid. Now, as the air in the upper chamber of the system is heated, the liquid is forced down through the tube into the container. The increased temperature of the air has caused the volume of air to expand, replacing the fluid in the tube with air. Some 15 years after Charles conducted his experiments, the French scientist Joseph-Louis Gay-Lussac noted that if a gas is held at a constant pressure, it will expand 1/273rd of its original volume if the temperature is raised from 0 degrees Celsius to 1 degree above zero. As you have already learned, this became the basis for the calibration of the Kelvin temperature scale. Gay-Lussac's law is expressed in the equation V sub 1 divided by V sub 2 is equal to T sub 1 divided by T sub 2. V sub 1 and V sub 2 are the two values of volume of the same confined gas, and T sub 1 and T sub 2 are the two different values of temperature. Most aerosol spray containers warn not to store above a certain temperature. This is another illustration of the effects of Charles and Gay-Lussac's law. If the temperature of a confined gas is changed while the volume remains constant, The pressure will also change in direct proportion to the change in temperature. As temperature increases, pressure increases. Aerosol cans could burst if the temperature is raised beyond a certain point. This relationship is expressed in the equation P sub 1 divided by P sub 2 is equal to T sub 1 divided by T sub 2. The general gas law combines Boyle's law and Charles' law to express a relationship among all three variables of pressure, temperature, and volume. The general gas law is expressed as the equation P sub 1 multiplied by V sub 1 divided by T sub 1 is equal to P sub 2 multiplied by V sub 2 divided by T sub 2. Remember, when using the formulas, temperature and pressure are expressed in absolute values. For example, we have 1,000 liters of gas at a temperature of 30 degrees Celsius and a pressure of 100 pounds per square inch gauge pressure. What would be the volume of the gas if we were to raise the pressure to 300 pounds per square inch gauge pressure and raise its temperature to 150 degrees Celsius? First, change temperature and pressure to absolute values. 100 pounds per square inch gauge pressure becomes 114.7 pounds per square inch absolute. 30 degrees Celsius becomes 303 degrees Kelvin. 300 pounds per square inch gauge pressure becomes 314.7 pounds per square inch absolute. 150 degrees Celsius becomes 423 degrees Kelvin. Substituting the values and solving the algebraic problem, our new volume becomes 508.8 liters. The ocean of air that surrounds us and exerts pressure upon us is actually a mixture of several different gases. About 78% of the air we breathe is nitrogen. Oxygen makes up another 21%. The remaining 1% is a combination of miscellaneous gases including argon, krypton, neon, and xenon. In 1801, the English chemist John Dalton discovered that the total pressure exerted by a mixture of gases that do not react chemically is the sum of the partial pressures of each of the individual gases. Dalton's law explains the need for oxygen systems or pressurization in high-altitude aircraft. The partial pressure of oxygen, being only 21% of total pressure, would not be sufficient at high altitude, where pressure is reduced considerably, to force oxygen from the lungs into the bloodstream. Above 10,000 feet altitude, the atmosphere must be supplemented with an oxygen system or cabin pressurization system to increase the total pressure and with it the partial pressure of oxygen. Early in the 19th century, The Italian physicist Amedeo Avogadro noted that equal volumes of almost all gases under equal pressure at the same temperature contain the same number of molecules. 1 volume of oxygen and 1 volume of nitrogen produce 2 volumes of nitric oxide, while 1 volume of nitrogen and 3 volumes of hydrogen produce 2 volumes of ammonia. Here's how that works. Oxygen atoms do not normally occur singly in nature, but are usually found in combination with other oxygen atoms to form molecules of oxygen, O2. The same is true for hydrogen and nitrogen atoms. The chemical compound nitric oxide is written in chemical notation as NO. By watching how the atoms of O2 and N2 combine, you can see that the result is 2 volumes of NO. Now, watch what happens when 1 molecule of nitrogen combines with 3 molecules of hydrogen. The result is 2 volumes of ammonia, NH3. Some review of the diagrams and formulas combined with study of your textbook material will help you more fully understand the relationship among pressure, temperature, and volume of gases.